continue the. Here we go. Okay, the view full screen mode. Okay, so welcome everybody again back to this class on data science, and we are going to finish today the support vector machine part. So this is the most technical part in this class, and I hope that I have not discouraged people, you know, by going through all the details. But I believe that it's important to understand the popularity of. In order to understand the popularity of this algorithm, one needs to see really the formulas that you use to you know, to classify, and you will see today why. So let me summarize the algorithm. The idea is very simple. So let's get back to the beginning. So remember what the assumption here was. So this was really technical. So the idea was that suppose you have data which is annotated and it consists of two classes, which will be called +1 and -1. So the red points are +1 points and the blue points are -1 points. And so presumably your data first approximation is linearly separable, so that you can find a hyperplane which is neatly separating the data in those two classes. And so then the question, of course, is to find this hyperplane. And once you have the hyperplane, you can classify any vector by saying simply by checking on which side of this hyperplane the data point unknown annotation lies. Okay. So
everybody. Sorry, Professor. Sorry for this.
Yeah. Okay. No problem. Okay. So so this is the starting point, and now it looks like a very straightforward and simple problem to do. And so what the idea is that you try to find two hyperplanes, H plus and H minus, so that the gap between the two classes is maximized. So if you find those two hyperplanes, then 2h is the distance between those two classes. You try to maximize that gap. And so that was the optimization problem. And those vectors which are lying on the hyperplanes, which are separating the plus and minus sets, they're called the support vectors. So that's the source of the name of the algorithm. And so then, of course, you cannot assume in general that your data is such that it's neatly separable. So you may have outliers which are not classified by any hyperplane correctly, and so therefore you introduce the slack variable, saying that, well, some of these data points may lie on the wrong side of the separating hyperplane, and so then you try to minimize the number of outliers, and therefore you are using the L1 penalty for the slack variable. Okay, so that was the idea. And so then we use the primal dual optimization algorithm, which is done for convex optimization problems with Lagrange parameters. So the Lagrange parameters are the dual variables. And then going through all this basic theory of convex optimization, we finally arrived to a let me see, reduced dual problem. So the reduced dual problem is a quadratic optimization problem with constraints. So you have a quadratic problem, B transpose G. B essentially is the quadratic part, and E transpose B is the linear part, and E here is a vector whose components are all equal to 1. I should have written it here, for some reason it is left out, but so remember, this E is just a vector with ones. And then you have inequality constraints for betas and an equality constraint, which is also important. And so then we try to, so well, if you have a quadratic optimization problem, you have to maximize a quadratic function. That's not hard because that's just a linear problem, but the constraints make it a little bit more complicated. And so what we did is we decided to, first of all, you would like, one idea is to optimize one coefficient beta at a time. Unfortunately, this is not possible because if you have this linear constraint, you see that if you fix p minus 1 coefficients, then the pth coefficient is also fixed. So you cannot optimize one beta component at a time, but what you can do is you take a pair of betas and then you optimize with respect to the pair. And that's exactly what we did. And so then we ended up to a algorithm. Okay, so I'll go to the algorithm soon. I want to point out this basic classifier algorithm here, and I want to make you pay attention to one particular feature here. So here is basically what we do in this algorithm. So we compute a matrix G, which consists of inner products of the data points, and then we find this vector beta. Once you have the vector beta, you define your Q, which is the vector which is perpendicular to the hyperplane, and then your classifier is simply you check the sign of Q transpose X minus B, where X is any data which is unlabeled and you need to label. Okay, so this is the whole algorithm, and so there is an interesting feature here. So all you need to know is how to calculate inner products. So the definition of G depends on the inner product of the data points, xj transpose xk. Okay, and so then the classifier C depends on an inner product of Q and X. So basically, if you have a way to calculate inner products, keep that in mind, you will be able to write this SVM classifier. So it depends only on a very simple idea of inner products. The only thing that you need really to calculate is the optimization of beta. So let's go and see how this beta was optimized. So here is the sequential minimal optimization algorithm, and again, if you look at the algorithm, let's go here. I think it's here. Okay, so in this algorithm, this is a very simple optimization algorithm, and if you have this matrix G, which is defined through inner products, then you can easily implement the sequential minimal optimization algorithm. There is really nothing else but inner products. So look at these BJs, for instance. That the definition of BJ depends only on inner products between the support vectors and the Q that you find in terms of this beta. Okay, so that's the important message here. And so I show you one example here, and I show how this works. So here's my test data. So I have generated the data which is almost separable by a hyperplane. So this is a two-dimensional data set. This is a very sort of trivial example. So because if you have this data set, you can place the hyperplane, which is a line, by hand here in this case. So you try to cut this data set into two so that your misclassification is minimal in terms of how many points you misclassify. Okay, so and here is the result. So when I run my algorithm finds a Q vector, which is this black arrow here, and the plane that is optimally separating these two sets is this dashed line here. And so you see that there are very few outliers, and the support vectors in the right panel are marked by squares around them. So you can think that the two separating planes that are maximizing sort of the gap are those who are passing through those support vectors. They don't perfectly form a line, but you know, almost, and that's just fine. So this condition, like a vector being a support vector, is a computational criterion, and so there may be some round of errors and computational errors. So they are not perfectly online, but they are more or less online. And so when I do that, I realize that the misclassification number of misclassified points is 16. And so here is a curve where I counted when I'm, you know, once you have this vector Q, what I did, I took a line which is perpendicular to this Q vector, then I was moving around this line, and I was counting how many points for my training set will be misclassified. And so this black curve here is telling how many misclassifications I have. And so the minimum, which corresponds to this this red vertical line falls on almost perfectly on top of the value for B that was based on the theoretical argument of using the support vectors. So this tells you that the formula for choosing B using the support vector is doing a great job, because you can't really you cannot improve the number of correct classifications by moving the plane. So they essentially coincide. So either way you use, either you try to minimize the misclassified points, or number of misclassified points, or you use the support vectors to set your B, you end up pretty much to the same value. So this is great news. Now, so when you see this algorithm, you say, okay, so great, but so what can I do with this algorithm? Because usually when you look at your data, you don't have this nice property that the data can be separated by a hyperplane. So linear separability is a very, very strong condition on the data, and it really is not common that your data is satisfying that. So let's go to the extension now. And this is really why support vector machine is so popular. So it was an idea of Vladimir Vapnik, who is the father, essentially the father of this support vector machine algorithm. It was his idea. One of his ideas is that you can actually generalize this support vector machine algorithm to cases where there is no obvious hyperplane that is dividing the data into sets. And let me show what I mean by this. So let's look at this data. So I have here a test data which I created, where I created two classes, the red class and the blue class. And instead of using a hyperplane, I took an ellipse. And I said, well, my points inside the ellipse belong to one data set, and the points outside to another. And then I added a little bit of noise to my data, so that some of them end up to the wrong side of the elliptical curve. So this is pretty well separable data, obviously, if you know that you're looking for an ellipse. So you could think that instead of trying to find a hyperplane, you could ask, well, is there a way to find other shapes, like ellipses, circles, parabolic curves, whatever you want, and separate the points in according to which side of that curve the point is falling. Now, for those of you who have been working with image processing, this may sound somehow familiar, because you have probably seen level sets. So you can think that this ellipse here could be viewed as a level set of a function. And so would it be possible to generalize the support vector machine algorithm so that it not only gives you the possibility to find separating hyperplanes, but it could divide your dataset in two level sets? So here is an example. So I have data which falls inside or outside a circle of radius. I believe it is square root of 3 here. Yes. And and then there's a little bit of noise in my data, so some of the dots are on the wrong side, but most of the time the dots are, I believe here they are actually all either inside when they're red or outside if they are blue. So now talking about level sets, suppose that I extend my data in a third direction. So this is a two-dimensional data. So now suppose that I embed my data in R3, so that the third component, x3, is the first component squared plus the second component squared. So what does that mean? It means that the data, which is originally lying here on the bottom on the two-dimensional plane, is lifted on the surface of this paraboloid surface. Okay. Now, if your data, instead of lying in the plane, is on this paraboloid surface, then of course you can find a hyperplane which is neatly separating your points in two sets. So this green green plane where z3 equals 3, it's neatly cutting the paraboloid so that the points which are lying on the paraboloid below that surface, this plane, they belong to the red class, and the points which are above the plane, they are outside the level set, and so therefore they are in the blue set. So here the trick is that if I extend my data into a higher dimensional space in a way that I know will produce this effect that the separating circle is going to become a level set, then I can do a perfect separation by using support vector machine. And so this is the idea. So this is called the kernel extension. So what did I do? Let's try to analyze it carefully. So I extended my 2D data in a 3D space using a so-called feature map phi. So in data science, this function phi would be called a feature map. So I extend my point xj, which is having two components, x1j, x2j, to be a new data point zj, which has three components, and the third component is this feature map evaluated at point x1, x2. And so now I have a perfect separation by the hyperplane, which in this previous picture was this green plane, HE3, 3. So that means I take the plane for which the third component equals 3, and that plane perfectly divides my data in two sets, and I have a perfect classifier here. So the question is, how does one guess the correct feature map? So now in statistics there is a technique which is called generalized linear models, where you are sort of using similar ideas that instead of linear regression you use some sort of nonlinear regression, and so this is somehow from the same family. The idea that I'm presenting here is somehow from the same family as generalized linear models, and so the idea is that since in general we don't know exactly what function feature map phi we should use, what we do, we define a lot of feature maps, and then we let the algorithm to decide which one of these feature maps it wants to use to separation. So that's the idea. Okay, so here is the idea. So let's suppose that instead of just introducing just one feature map phi, I make a generous expansion of the data. So instead of generating my data, generalizing my data from 2 dimensions into 3 dimensions, I say I'm generalizing my data from 2 dimensions into k dimensions, where k can be really, really large. Actually, at the end, we make k to be infinite, as you will see. Okay, so we are doing this generous expansion of the data. So we define k feature maps, phi1, phi2, etc., phi k. And then we send our data points x, which lie on the low dimensional space, into this high dimensional space of k components. And so we define a new data set to be the z points, which are phis of x. And so in the previous example, we had n equals 2, so we had 2-dimensional data. And so we decided that the first feature map phi1 was just giving the first component. The second feature map was giving the second component, and the third feature map was giving the sum of the squares of x1 and x2. So let's go back so you see that this is what we had. So we had, here's the first feature map. That's simply picking the first component. Second feature map is picking the second component, and the third feature map was taking this first square plus second square. So here we had 3 feature maps where phi1 and phi2 were just picking the components, and then we had the third feature map. But in general, you can have a huge amount of feature maps, and then you just let the algorithm decide which one of those feature maps it wants to use to do the separation. So that's the idea. And so here is a feature map extension of the support vector machine. So this is how it works. So given a dataset x1 with classification plus or minus 1, etc., x2, xp with classification plus minus 1, we choose these feature maps. So phi here is a vector. Now, so phi is a vector, so it has components phi1, etc., phi k. Okay, so this is now a data point in a higher dimensional space, Rk. So then what we do, we take the support vector machine and we try to find an separating hyperplane H in this higher dimensional space. And so once you have this separating hyperplane, then if a new data point comes, which you need to classify, so what you do is you extend your unknown x into this higher dimensional space. Then you use the separating hyperplane that you just found, and then you check on which side this extended data point lives. And so then you classify accordingly. So this is the whole idea here. So it's a very straightforward and beautiful idea. And so let's think about this a little bit. So it turns out that, again, we don't know what feature maps we should use, right? Because the success of this algorithm depends completely what sort of feature maps you would use here. So my first guess would be let's use polynomials. So okay, so my feature maps could be polynomials of different order of my unknowns, and indeed you can use polynomials. But then you have to decide where you cut. So how high dimensional polynomials, how high order polynomials you are going to use. So there's always this question how you choose your feature maps. But so let's look at first how it looks like if I define those feature maps. If I define first the feature map, so how does the algorithm change? So I take k feature maps phi j, which are real valued functions, and then I vectorize this, and so that these are the components of my phi vector. And so now let's look at the inner product. So now this phi x is the extended data point corresponding to x, and phi y is the extended data point for data point y. And so now the inner product is simply the sum of these feature maps, of course. And so what I'm going to do, I'm going to denote this finite sum here by k, which is a kernel function. So this kernel function here is a function which is from Rn by Rn to R. So this kernel function is defined in the original data space Rn. And so then if you look at this k here, it has certain properties. So first of all, this kernel function is symmetric, meaning that if you swap x and y, you get the same value. So kxy by definition is the sum of phi jx, phi jy. Okay, now of course you can change the order of the product here, and you get phi jy, phi jx, and so you see that the kernel function is symmetric in the sense that it gives the same result if you change the order of x and y. So that's the first observation here. It has further properties. It is so-called positive semi-definite kernel. So let's look what that means. So my k has let me see, it has m component. I have an indexing problem here, so I should have, instead of m, I should use k. I apologize for. No, sorry, this is correct. Yeah. So take any. Yeah, it was nothing. So sorry. So take any vector which is in Rm, where m is arbitrary integer, and so then define a matrix Kij, and this Kij is this kernel function which is defined on arbitrary points xi and xj. So this xi and xj, they don't need not to be data points. They are just some points in Rn. So I'm picking disjoint points xi and xj from my Rn, and I'm forming a matrix Kij so that the ijth component of this matrix is simply this sum here. So it is the kernel function evaluated at points xi and xj. And then I'm looking at this quadratic form here, which is V transpose K, V, which by definition is simply this double sum, where I take the components of V on both sides and then I make a matrix product of this. Now, if you look at this quadratic form here, and you use the definition of your Kij, which is given in the second line here. So then if I reorganize my computation so that I'm first summing over I, so that I give a linear combination of these components of Vi, and then I'm summing over J, which is the linear combination of the components Vj. So then you see that in the third row, the expression in parentheses is the first parenthesis and the second parenthesis is the same, because I'm taking the sum over all points xj and all components of Vi. So I and j are just summation indices, and L is the same for both of them. So those two expressions are the same number with different summation index only. So what I can do is I can replace my I for in the first sum by j. So then you see that I have the same number multiplying itself, so this is a square. And so then you see that my V transpose KV is a sum of squares of some numbers. And so since the squares of some numbers are non-negative, so the sum is also non-negative. And so we see that this K matrix defined by using this kernel function is a positive semi-definite matrix. Positive semi-definite matrix, recall, is exactly a matrix for which V transpose KV for V non-negative, well, non-zero is always positive or zero. Okay, so this is an observation, and so this gives us a hint that actually we can generalize the idea of using these feature vectors into using kernels. So notice, if I have a finite number of feature vectors, I can always define the kernel K. So this is the kernel in the last line, or in the middle line. So this is the definition of K in terms of feature vectors. But actually, what I would like to do is the opposite. I would define a kernel and then let the kernel define the feature vectors. So that's much more flexible way of approaching problems, because you can simply define kernel and let the kernel decide what the feature vectors are, rather than giving a long list of feature vectors and then putting together a kernel. So this is a computational trick. So I'm doing the following. So suppose that you are taking an infinite amount of feature vectors, phi L, where L goes from 1 to infinity. So suppose you take all the polynomials. Now you can weigh your polynomials in such a way that the sum here, L runs from 1 to infinity, is convergent. So you put some weight which is going to 0 when L increases, and so then you can basically take all polynomials and define a kernel function k x y in this way. So now you are really extending your data space into an infinite dimensional space, or a Hilbert space if you want. Now, suppose you have a kernel function kxy. It doesn't have to be of this form here a priori. So you take any kernel function. Let's take the exponential or a Gaussian kernel function, or whatever you want to choose. And so then you look at the kernel function. We say that the kernel function is symmetric if it satisfies that if you change the order of x and y, you get the same value. Okay, so this is symmetricity of the kernel function. Now the other thing is that we say that the kernel function is positive definite if the matrix that we form by evaluating the kernel function in some points in Rn So this matrix is positive semi-definite. So this is a little bit confusing because you know, coming from linear algebra, you would say, okay, so if the matrix is positive semi-definite, let's call the kernel function positive semi-definite. However, the use of the words here is a little bit different because this kernel function idea comes from approximation theory, and so people have used different concepts there. So we say that the kernel function is symmetric positive definite kernel. If it's symmetric, and if the matrix that you form by choosing a finite number of points and evaluating your kernel function at those points, if that matrix is positive semi-definite. Okay, so if I have a function kxy, which is of this form, L runs from 1 to infinity, you have feature functions phi L, and so you form your kernel function using this this symmetric product, sum of the products here. So then you get a positive definite kernel. So what is the proof? So let's go back here. If my m is infinite here, nothing changes because in those sums in parentheses, my I runs from 1 to infinity and j runs from 1 to infinity. The only thing that I need to be sure is that this infinite sum is convergent. But I can always weigh my feature vectors in such a way that I guarantee that the infinite sum is finite. And actually I have to do that weighing already when I'm defining this kernel function here, because the kernel function, to be well defined, I of course want that it has finite values. So my feature vectors are, my feature functions are scaled in such a way that my k is convergent. So using an infinite amount of feature vectors, I can always define a kernel, and that kernel is positive definite, symmetric positive definite. And what does mean positive definite? Here is the definition, and we just check that using this definition, I certainly get the symmetric positive definite kernel. We're so far so good. Now, what if you give me a kernel function? Do I always find feature vectors? Turns out that yes, you can do that. So there is a famous theorem which is called Mercer's theorem. And so here is one version of Mercer's theorem which says the following. So suppose you give me a symmetric positive definite kernel function. Then there are feature vectors phi L, infinite amount of feature vectors, so that this kernel function can be expressed as an infinite sum of these symmetric products of the feature vectors. So what have we so far? If you have feature vectors, you can always define a kernel, and the kernel is symmetric positive definite kernel. Conversely, if you give me a symmetric positive definite kernel, I can always define, by Mercer's theorem, there is always an infinite amount of feature vectors, so that my kernel can be expressed as a symmetric product of those feature vectors. So I can now choose whether I define the feature vectors, which may be difficult because I have to have a list of feature vectors, infinite list of feature vectors or finite list of feature vectors, but I have to choose them. So polynomials, for instance. There's nothing wrong with choosing the polynomials, but the problem is that in order to guarantee that your kernel function is convergent, you have to find appropriate weights for your polynomials so that you get convergent. Much nicer would be that you give the kernel function k, and you don't actually care what these feature vectors are. You know that they are there. You know that there's an infinite amount of feature vectors. And if needed, Mercer's theorem tells you that you can always find them. Mercer's theorem doesn't give you the algorithm to find them, but you know that there are infinite amount of feature vectors that correspond to your kernel. So now what we do in this support vector machine context, we use the so-called kernel trick. So people are talking about kernel trick, and this is what it is. So you pick a symmetric positive definite kernel k, and then you replace the original inner product in your data space, x transpose y, by kxy, without thinking what the feature functions are. And then you take your support vector machine algorithm, and every time you need to calculate an inner product, you replace it by kxy, and that's it. So this is the beauty of this kernel extension. So you derive the support vector machine algorithm using inner products of your data points. And then at some point you say, well, I want to do an extension into an infinite dimensional feature space, but I don't want to define those feature vectors. What I do, I pick a kernel, and every time I see a x transpose y, I replace it by kxy. And that is the inner product of the data extended to the feature space. And so then you are done. And so you let the support vector machine algorithm to decide which features it is going to use to separate your data. So the whole story is here. So that was an observation that made really the support vector machine one of the most popular, let's say, classifier algorithms, because now you don't any longer need to assume that your data is linearly separable. Rather, you say, I'm looking for a level set function, which I don't know what level set function I'm looking at, but I'm trying to find the separation so that the separating curve, which is no longer a line or a hyperplane, the separating, let's say, manifold in the data space is a level set of some unknown feature vectors, which are feature vectors that constitute this kernel. And so that's what people have been doing. So let's look at some popular kernel functions that are commonly used in this context. Now, if you define your kernel to be x transpose y, of course, then you didn't do any extension, because now your feature vectors are just the components of your data. And so this is not what people use, because if you use the first one, there's no gain. So you can use this would correspond to data which is linearly separable, and you're looking for a hyperplane. So you're in the original support vector machine algorithm here. Polynomial kernel, that's rather popular already. So you take lambda plus x transpose y, and then you raise it to the power m. So why is this called polynomial kernel? So of course, if you take this binomial form here, and then you extend it using the binomial formula, you see that your k is a linear combination of x transpose y's to power m, and so then you can use the multinomial expansion, and you see that your kxy is a linear combination of polynomials of the components of x and y. And lambda here is some sort of scaling factor, which you need to choose. So in choosing these kernel functions, you have to choose the sort of the width of the kernel function. So that means how far away points are sort of interacting. So choosing the kernel function, you're basically saying that if you have far away points, their inner products in this feature space is going to be 0. So they turn out to be orthogonal vectors in this feature space. And so the wider your K is, the less you have orthogonal components. The narrower your K is, the more you have, let's say, independency between your data points. And so this lambda here is some sort of correlation length, if you want. There's a little bit of adjusting here that you need to do. Gaussian kernel. So how does Gaussian kernel look like? So well, you take the usual Gaussian kernel, and sigma squared here is the variance of the Gaussian, or the width of the Gaussian. And again, if you make sigma large, then points which are far away from each other have significant effect on each other, so they are not orthogonal. If you take sigma really small, so then your Gaussian is really narrow, and 2 points which are, let's say, 3 standard deviations from each other, they're essentially orthogonal now in this generalized sense. So orthogonality now means that the kernel function of x and y equals 0. Okay, so then this is a popular popular kernel. Laplace kernel is another popular kernel. So you take exponential of 1 over lambda, and then instead of the norm squared of x minus y, you take just the norm of x minus y. And so again, choosing lambda judiciously, you can regulate how orthogonal, let's say, the data points which are far away from each other are. So these are probably the three most popular selections of kernel functions. And so now you can go to the support vector machine algorithm and read it through. But every time you see an inner product, you replace it by the kernel function. So here is I just copied verbatim basically the support vector machine algorithm, and then I do exactly what I said. So we start with the data x1 to xp, and with binary annotation. And actually, I don't need this y, so you can strike through this yj because we don't need it anymore. Okay, so and I take a symmetric positive definite kernel function instead, and a parameter lambda, which is defining my oh no, sorry, what am I saying here? So let me see. There's no penalty. So sorry, I need to correct this. So this is not. Oh yeah, well I need this lambda. So this lambda is not related to the kernel function. It is related to the support vector machine algorithm. So we had this lambda which is penalizing the slack variables. Okay, so let's start and take the matrix G. So remember how this matrix G looked like. So it was the inner product of yj, yk. So that gave you the jkth component of the matrix G. So what I'm doing, I'm replacing the inner product of xj and xk by k of xj, xk. So I'm just evaluating my kernel function at that point. So now this is playing the role of inner product here. And so then I have this matrix G. I go to the sequential minimization algorithm, and I find the betas. And remember, this beta minimization algorithm depends only on the matrix G, which I have defined here. And basically, it was just a quadratic optimization problem with constraints. And so you do this optimization, and you have this lambda which is appearing in the constraints. You do this optimization, and you find your betas. Okay, so now you have if this would be the support vector machine, you would have your vector q. So you can define your vector q, but we are doing it implicitly because we don't want to define the support vector or the vector q in Rn. We want to use a quantity that is defining the inner product with q. So remember, when we did classification, we were only calculating inner products with the unknown x and q. So we define a substitute for q by saying that we only need to define how q acts through inner product in the feature space. Well, it acts through the kernel matrix qx. And so here is my definition of what this q, k, q, and x means. So instead of the inner product with the linear combination of these xj's and x, I'm saying that this generalized inner product here is simply that you calculate the inner product of xj and k, and then you sum those inner product multiplied by beta j cj, where beta j's are found using this minimization algorithm. So this is the inner product with k with q, and so then you identify support vectors. Remember, that was related to the Karuskul-Tucker algorithms conditions, and then you define this b by choosing it like this. So your b is the mean of the inner product, the generalized inner product of q and xj, which are the support vectors minus their classification. So what I have done here, I have simply copied SVM algorithm, and every time I see an inner product, I replace it by this kernel. And so you see that this is really straightforward extension computationally, but the effect is dramatic because now you are doing the classification not in the original data space, but in the feature space. And the beauty is that you don't really care what the feature space is because you have this kernel. So you don't need to go and use Mercer's theorem to find those feature vectors. You just use the kernel, and in the back of your mind, you know that there are some feature vectors. So here is the example. So I take the data that I originally showed you. So suppose I want to classify my points here. So this is my training data, and so I'm using now a Gaussian kernel, and I'm running the kernel version of the support vector machine, and I see how well I can separate these two data sets. And when I do that, so I remember that I was thinking, so how should I choose the width of the kernel function? And I don't have here the numbers how I chose it, but it was pretty straightforward. So I simply tried a couple of different values, and this algorithm is rather robust with respect to the parameter controlling the width of the kernel function. So here is the result. So let me see. So the so-called optimal hyperplane, yes, the optimal hyperplane corresponds now to this ellipse here. And when I do the classification, let me see. So look, here are the original classifications. So red is class +1 and blue is class -1. And so in the next picture, so look at this picture. So the color indicates how my points are classified. Okay, so this is the true classification. In the next picture is the classification that my algorithm does. So you can take, for instance, look at a point which is red here outside this ellipse and see how it will be classified. And you see it is classified to blue. So the result here is the color coding here corresponds to my classification. So everything that you see marked with red has been classified to class +1, and everything that is marked by blue is classified to the -1 class. And so you see that there's a little bit of misclassification, but the overall picture is really good. So here I have plotted the original ellipse, and so originally the points inside should be more or less in one class, and those outside should be in another class. What these little squares here are, they are the support vectors. So now I have a lot of support vectors, and so you may wonder why these support vectors are not lying around this ellipse here, this level set. And the reason, of course, is that I don't have any idea how the points are distributed in the feature space, because I don't know even what the feature vectors are. So you can imagine that there is some sort of hypersurface or let's say a manifold in this high dimensional space. And when you're slicing your data with a hyperplane in this high dimensional space, some of the points are lying close to the slicing hyperplane. Where they lie actually in this picture is some of them are far away from this level set curve. Some of them are close to the level set curve. So this is not an indication that my interpretation of the support vectors would be somehow flawed, because I have no idea how the picture looks like in a high dimensional space. But so what is remarkable here is that the overall classification is pretty much what I wanted. So this is the truth, and this is the classification. So there are rather few misclassified points here. So this is an example of how this support vector machine works, and you really can can see how this kernel extension helps you to generalize the algorithm from the very restrictive case of linearly separable data to more generic cases. So of the support vector machine, I don't have any let's say real example here. So this is sort of an artificial example so that you see how it works. But let me say a few words about let's say of the criticism of this algorithm. So one thing that people are complaining a little bit is that support vector machine doesn't really give you an interpretation of what your classification is based on, because the classification happens in the high dimensional feature space. So I saw an article where this support vector machine was tested with data where they were looking at internet posts, I believe, in some sort of chat site, and so they were trying to classify the text based on the contents. And so the idea was that they are seeing, I believe that the question was which ones of the posts were related to religion and non-religion. So that was the question. And support vector machine did a rather good work on, classifying correctly the test data. So then they went and analyzed based on what the classification was done. So what did support vector machine use as, a clue whether or not the data point belongs to a class 1 or class 2? And it turned out that it actually classified by who had posted. So basically the contents was irrelevant. So this is the danger of these blind classifiers. When you're using a blind classifier, you may have a good result as far as the classification is concerned. But if you don't know what the classification is based on, you may end up having a classification which is based on completely irrelevant factors. So there's a famous example from, I think, from the from 90s maybe. So this was when the neural network started to really, become popular. And so in this classification problem, I think this was related to the US military use of this classifier. So they were looking at photographs of tanks. So they wanted to classify from the photograph whether a tank was an American tank or not an American tank. Okay, so that's a simple question. And so they had the training data, and the classification was rather perfect. And so then they started to analyze based on what the classification was done. And it turned out at the end that the American tanks had been photographed in sunshine and the other ones in a cloudy day. And so the classifier did a perfect job, but it didn't recognize at all that the object that you were looking at, it recognized the lighting. And so it did a perfect classification, but it classified the pictures according to whether there was sunshine or not. And so this is really the danger when you're using these sort of blind features. You don't know what features you're using here. Your classifier can do a fantastic job as a classifier, but you may not know what the classification basis was. And so this is really one danger of these classifiers. So we are going to, at the end of this, it's not today, but starting on Thursday, we are going to look at another classifier, which is the tree-based classifier. And so one thing about these tree-based classifiers is that you know exactly what features you're looking at. So tree-based classifier tells you what is the important feature and what is the next important feature, and so on and so forth. And so you get a sense of what your classifier is doing. So the interpretability of classifiers is one of the big discussion issues in in data science nowadays. And so this is the caveat. So there's nothing wrong with support vector machine if you don't really care what the classification is based on. So if you're using sort of, let's say, commercial data and you want to sell like products to people, you don't really care why the selling works well for this group and not for that group, because the classification doesn't know that. However, if you are classifying, for instance, medical data, malignant, benign tumors, for instance, you really do want to know why the classifier recognizes a point in one group and a point in another group. And so using a blind classifier may be dangerous. So this is the danger of using these neural network methods, for instance, in medical science, in medical imaging. People usually want to know why there is a difference between malignant and benign case. And you don't want to end up having the situation that the classification is based on, for instance, on the protocol of collecting the data. That would be a disaster, because of course then you can, end up misclassifying people completely by changing the protocol. So that's really the danger. Okay, so this is the last slide on support vector machines, and I hope you got an idea how this kernel extension works. And I would suggest that we have a break as usual. Let me try to. So it's 3 minutes to the hour. So we could continue at 4:10. So 10 minutes after the hour. So let's have a 13 minutes break, and so then we move to another topic. All right. Thanks for this first hour, and see you soon.
Okay. Thank you.
Thanks.
Hi, Professor.
Hey. Hello.
Sorry, Prof. There is a question for you in the chat.
Okay, I'll check it. So sorry, yes, I will go to the chat. So after you run the kernels, how do you look for the criteria in which the classification was done? I guess depends on the choice of the kernel. So this question is a really good question. So there is not really a simple way to look at the criteria. So the paper that I was referring to was a paper whose title is nice. I like it. It says, "Why should I trust you?" So if you go to Google Scholar and you type, "Why should I trust you?" you find this nice article where they were looking at these examples of that I referred to. So the idea usually is that you have to use some other method which is criteria based. And so you use the classification that you get by your blind method, so to speak, with a support vector machine method. And so then you try to find a criterion using your criterion-based method that classifies similarly to the support vector machine. And so then you compare, and that gives you an idea what criteria was important for the classification that you got from support vector machine. So support vector machine itself does not give you really information about what the classification was based on. So you have to use an additional other layer of classifier to figure out what the classification was based on. So this is one of the active research areas in data science, and it is particularly important in neural networks, because in neural networks you have no idea what the classification is based on. So you have these layers and layers of convolutions and ReLUs and whatnot, and so then you get the classifier, and the classifier may be nice, but you don't know what the classifier was sensitive to. So in order to check what the classification is based on, you really have to use some other method where you know what the classification criterion was. So tree-based methods is one way to check. So therefore I think the tree-based method is really an important method, because it is often used as a check. And so that's the topic after I have finished the topic of today, which is image mining. Okay, so I hope this is giving some sort of sense what is going on here. All right, so let's move to the next topic. So image mining. So this is what I'm going to talk about. So in this section, I'm looking at grayscale images, although all I'm saying about grayscale images can be extended to color images, because a color image, if you use, let's say, the usual color coding, for instance, using the RGB, you can think that you have like 3 grayscale images. And so instead of having 1 pixel value, which is this grayscale value, you have 3 values, which is the RGB value. And so when you see what I'm saying, you probably see how you could extend things into this 3-dimensional case. Although sometimes it's not obvious, but you know, for simplicity, I'm trying to keep this section transparent and simple, and so therefore my images are simply grayscale images. And so what is a grayscale? Grayscale is a number between 0 and 1, or 0 and 256, or whatever you want to use. 255 maybe if I use 0 for black. But so anyway, so you have a range of minimum and maximum. So minimum corresponds to black and maximum corresponds to white. So I'm often scaling between 0 and 1 because that's sort of nice standard way of scaling. Okay, so grayscale image, you can think that if you have n by m pixels, so then your image is just a matrix where you have non-negative values corresponding to the grayscale at each corresponding pixel. And so that's the simplest possible way of representing an image using the grayscale matrix. And this is what I'm assuming here. Now, the value of the grayscale in your image may be informative. So I give you an example. So if you think of CT images like X-ray images. So radiologists know what the grayscale value signifies. They usually are referring to Hounsfield units. So Hounsfield units means the absorption coefficient of a pixel. And they have a lookup table where you go and see what a grayscale value typically corresponds to. So if you have a, let's say, a picture like here, a brain scan, so you can go and see what the grayscale means. So there's white matter, there is gray matter, there is bone and so on and so forth. So looking at those pixel values, you get already information what you're looking at. If you look at another medical imaging application, MRI, the magnetic resonance imaging, here the situation is a little bit more complicated because MRI is not a quantitative imaging technology. So if you take the value of the pixel, it doesn't tell you what you're looking at. So it is relative to the image. And so MRI makes perfect images, beautiful images, but the pixel values per se are maybe not so informative. And so one big issue in MRI is to use to make it quantitative so that the pixel value would tell you what you are looking at. So that's important, for instance, when you are looking for tumors. So you would like to know whether an inclusion is a tumor or not. But usually you have to go and take the biopsy to understand what you're looking at. But at least you know where you look at. So this is not to say that MRI is not a good technology. It's a fantastic technology. But X-ray has this extra advantage that you even know what you're looking at. Now, so if you look at this grayscale image, you can do quite a bit already by just looking at the grayscale. So here's an example. I have plotted a histogram of different grayscales. So each column here in my histogram is telling how many pixels I have having that particular grayscale value. And so if you look at this histogram, you see that there is some sort of dip here. So you can think that there are two peaks which are overlaid here. And so if I cut the image along this dashed red line, and I'm coloring the images whose grayscale value is below that value, and I'm coloring the images whose value is above this value, I get these two images below. So the let me see, the higher value is the one which is on the right, and so it seems that it's pretty much separating, let's say, at least the white matter, but a little bit of the gray matter too. But it's not really clear what I'm looking at. So some sort of separation of pixels in two I get, and it's some sort of primitive, let's say, separation of the image into two groups. But so single pixel values are not that informative. But if you look at the neighborhood of each pixel, you get already much more information what you're looking at. So a good example is that if you look at the synthetic aperture radar image in remote sensing, so our eye is rather sensitive to texture. So if you look how the SAR image of a forest looks like, and how the SAR image of an open field looks like, our eye is pretty sensitive, and we see rather clearly where the forest ends and the field starts, or the lake, or whatever you're looking at. If you look at single pixel values, you pick a pixel from each one of those areas, you basically have a random number. And looking at the pixel value itself, you don't really tell what you are looking at. So single pixel values are not informative. Single pixel values with a little bit of surrounding gives you already much more information about what you're looking at. And so this is the idea of the technique that I'm going to talk about. So this is the gray level co-occurrence matrix that I'm forming from the image. So you have an image, let's say you have several images. All the images are of different size, first of all. Some is 100 by 100, and another one could be 2000 by 2000 pixels. You would like to compare those images. So you would like to standardize the images somehow, making them to be representative of a data vector of the same size. And so this gray level co-occurrence matrix is doing that. So it is standardizing the images so that you have comparable data vectors of the same length without eliminating, data. And so you want to get rid of the differences in the number of grayscales. So one picture may have been taken with higher resolution with respect to the grayscale, different pixel numbers, different aspect ratios, etc. You don't want those to be critical factors when you're classifying your images. And so what we first do, we get rid of the variability of the grayscale. So we are scaling our grayscales in all images so that the grayscale values are between 0 and 1. So you take your image, you calculate the minimum and maximum of the grayscales in that image, and then you are scaling down or up the grayscale values so that the maximum corresponds to 0 and the minimum maximum is equal to 1 and minimum to 0. Or it could be somewhere in between. It doesn't have to fill completely the interval, but the important thing is that the values are between a minimum and maximum value. So that depends on a little bit on the application, how you scale your grayscales. Okay, so first of all, we want to standardize the grayscale resolution. So what we do, we decide we are going to look at k different gray levels. So you take the interval from 0 to 1 and you divide it in k equally spaced intervals. Okay, so you say I'm going to look only on k different gray levels. This k could be 8, it could be 100, it could be 50. So you decide how you scale your grayscale. You divide the interval into k subintervals of equal length, ij. Then for each pixel, you ask in which interval your grayscale falls, and that's the classification of that pixel. So we are classifying each pixel depending on which interval the grayscale is in. And so that's the reduction of my image into an image where the number of grayscale is simply from 1 to k. So now my grayscales are integers. Notice, I'm saying that my Cij is L if the true grayscale Iaj, so this is the scaled grayscale, is in the interval IL. So I'm classifying each pixel into one of the classes from 1 to k, depending on which subinterval the grayscale falls. So for each, I have an n1 by n2 image, and so my new matrix C is an n1 by n2 matrix where the values in that matrix are integers from 1 to k. So this is the first standardization of the image. And so then we start defining what is known as the co-occurrence matrix. As I said, the pixel value itself is not that informative. So you can have in an image 2 pixels which are representing completely different things, and yet they have the same grayscale value. So you can think, let's talk about this synthetic aperture radar image. So you can have a pixel in a forest which happens to have a pixel value which is exactly the same pixel value that you have, let's say, on a pixel that belongs to a lake. So just looking at the pixel value, you cannot tell which one is representing lake and which one is representing the forest. So you have to go and look at the picture. And if you don't have any quantitative method, you have to rely on your eyes. And your eyes are saying that the texture around that pixel looks different. So, okay, so if this texture here is flat, so that means that it's probably a body of water. And if the texture around that pixel is rough and looks like trees, you know, then they say, well, this probably is a forest pixel. So we want to do this quantitatively. We don't want just to rely on our eyes on this. So what we do, so we have this coarse and gray level matrix, and then we define, we choose two offset parameters, mu and nu. Okay. So how do we choose these? We'll talk about that later. So I choose two integers, mu and nu. And at the end of the day, I can also choose several of them, but at this point, I'm only choosing two numbers. Let's say 1 and 3. You decide it. And so then we define a so-called gray level co-occurrence matrix, G, which is a function of these two offset parameters, mu and nu. And notice this matrix, regardless of what your image size is, whatever your N1 and N2 are, these matrices are always K by K matrices, where K, remember, was the number of gray scales that you had in your coarse and grayscale matrix. So K is this number here, the number of subintervals that you have. So how do you do this gray level co-occurrence matrix? So you pick two gray level index pairs, P and Q. So P is any value between 1 and K, and Q is any value between 1 and K. Okay. So then you say that in your gray level co-occurrence matrix, the PQth component, GPQ, is the number of times when the gray level in a pixel ij is P, and the gray level in a pixel with offset mu nu is Q. Looks really obscure. So when I read this, if I don't know what I'm doing, I don't understand this definition. So I will make it clear to you just by looking at an example, just a moment. But so I give you the definition. So PQ is referring to two gray levels. So this gray level co-occurrence matrix is K by K, because you can take all possible combinations of gray levels. Okay, so therefore this G is K by K matrix, and the PQth component refers to a pair of two different gray levels. And so what you are doing, you are checking how many times there is a co-occurrence of P and Q in two pixels, so that the other pixels is obtained from the other pixel by moving it by the defined offset mu nu. So now you get the matrix which has integers in it, because you calculate how many times the co-occurrence of these two grayscales appear. And since you may have different sizes of images, in one big image this number may be large, and the smaller image this number may be small, and so then you normalize your G. So you divide by all components of your G matrix, and so now you have a normalized matrix G, and so that's your gray level co-occurrence matrix. And as I said, this definition here is really obscure if you haven't done this ever. So let me try to go through this with an example. So I think this is the way you can visualize it. I take a small image matrix, and then I'm showing how the co-occurrence matrix look like. So my image C here is this. So I have started with an image of 1, 2, 3, 4, 5 by 1, 2, 3, 4, 5. So I have a 5 by 5 image. So I have a really tiny image which has only 5 pixels. Okay. So this is really a toy example. So take an image with 5 pixels, 5 by 5 pixels, 25 pixels. Now I have coarsened the grayscales so that there are only 3 possible grayscales, 1, 2, and 3. So I have divided the interval from 0 to 1 in 3 equally long subintervals. Then I'm asking in which of those intervals my pixel value lies. And so, for instance, pixel 1, 1 lies in the first interval, so I put 1 there. Pixel 2, 1 is lying in the second interval, so it's between 1/3 and 2/3, so I put 2 there. And let's say the pixel 5, 1 is having a value which is between 2/3 and 1, and so I put 3 here. So this is the coarsened image. So I'm only classifying each pixel in which one of those intervals it's lying. So then I'm deciding what my offset parameter is. So here is mu is 1 and nu is 0. So I'm the one who is deciding what mu and nu are. So I have decided here that mu is 1, nu is 0. So when I say mu equals 1, it means that I'm moving in my image only 1 step down. And nu is 0, it means that I take 0 step to the right. So mu is what my offset is when I'm moving down by 1 pixel, and nu is the offset moving to the right. And so when I say nu equals 0, there is no offset in the horizontal direction, but there is offset of 1 in vertical direction. And then I start to count how many times I have different pairs of grayscales in this picture. So let's start with 1, 1, G1, 1. So I'm looking at this quantity 4. So 1, 1 means that I take 2 grayscale values, 1 and 1. And I'm asking how many times I have the number 1 appearing above another one, because that's my offset. My offset is I go 1 step down. So how many times I find a pair of 1, 1, so that the ones are 1 on top of the other. So here is one occurrence of such pair of 1. Here is another occurrence of such pair of 1, third one, and fourth one. So in this coarsened image, there are 4 times ones appearing so that the other one is obtained from the first one by doing the offset 1 step down. So I put 4 here. So now I go to the pixel 1, 2. So I'm asking how many times I have 1 in a pixel, and in the offset pixel I have 2. So here is 1 and the offset pixel is here, and I have 2. So here is 1 occurrence of the pair 1, 2. Here's another occurrence of 1, 2. So here is 1 and here is 2. Here is 1 and here is 2. Here is 1 and here is 2. So I realized that 4 times in this coarsened image, I have 1 in a pixel, and in the offset pixel I have 2. So I put 2. I put 4 here. Let's look at this quantity here. So this is 3, 1. Now I'm asking. So I take a pixel with value 3, and I'm asking how many times there is 1 below a 3. So how many times do I have? So here is 3 and 1, and here's 3 and 1, and that's it. So there are 2 of those. So I put 2 there. So I'm doing this for all pairs of grayscale values. And since I only had three grayscales in my coarsened image, this matrix is going to be a 3 by 3 image. Then I take sum of all these values, it's 20, and I'm dividing by 20, and that's my G10 grayscale co-occurrence matrix of the image. And so this matrix somehow tells me something about the text structure in this image. So it tells me how the different colors are being neighbored in my image, and so that's something that I'm interested in when I'm classifying, for instance, the images. So here is another example. So I have taken the offset 1, 1. So now my grayscale co-occurrence matrix is 1, 1. And so that means that I'm making a shift 1 down, 1 right. Okay. And so let's look at the component 1, 1. So there is, I have written 4 here. So the blue arrows are the ones that correspond to co-occurrences of 1 and 1. So here is 1 and 1, so that's 1. Here is 1 and 1 in the diagonal position again, here and here. So I have 4 times those, and so I get 4 here. Now I'm looking at the co-occurrence of 1 and 2. So I'm looking at this component, 1, 2 component in my matrix. So I need to find the pairs 1, 2, which are appearing with a diagonal shift. So 1 down, 1 right, one right. And so there are only 2 of them which correspond to these red arrows here. So I put 2 here, and so on. So I'm filling this matrix with those numbers, and then I'm dividing by the total sum. And so that's my grayscale co-occurrence matrix 1, 1. So as you see, the definition that I gave you here, so this is kind of obscure when you read it, but when you see this idea how you are moving from pixel to pixel and comparing the grayscales, then you see what this really means. And so now you can easily think that this grayscale co-occurrence matrix is sensitive, for instance, to the alignment of the colors. So if you have a striped image and the stripes are horizontal, or the stripes are vertical, or the stripes are diagonal. So all these cases will lead to a different co-occurrence matrix depending on how you choose your offset values. So if you're moving from up to down, or you're going from left to right, or you're going diagonally, and you don't have to move just 1 step. So you can take, let's say, 4 steps down and 3 steps to the left. And this is a little bit of experimentation to see what offset parameters give you most information about the image, but the basic idea is always the same. So now, for those of you who are familiar with the so-called CNNs, the convolutional neural networks, you see that there is a certain similarity here with those CNNs. So CNNs are used for classifying images. You know, whether your image has a boat or a cat or a person. And so what these convolutional neural networks are doing, they are coarsening the images, and then they're calculating some sort of convolutions of the images. And so the convolutions are sort of similar in some sense to these offsets. And so there is a certain similarity with neural networks. This is rather straightforward way of creating a standard representation of an image. So here is an implementation in MATLAB. So it looks like this is something complicated, but so here is one way of doing it. So here is your C. So this is the original C, and I'm using the same C that I had before. So I had 1, 2, and 3. And so then I'm using, let's say, if my shift is 1, 1, as I did in the previous case. So what I'm doing, I'm shifting the whole image 1 step to the left and 1 step up, so that effectively, when I'm comparing with this original image, I'm superimposing the 2 pixels that I'm comparing. Okay, so I'm doing this by defining a matrix which is full of not the numbers, first of all. So the C shift is a matrix full of not the numbers. And then I'm replacing the components by this line here with the values which are shifted by 1. And so what I did here is that I shifted all these numbers 1 step up and to the left. And so here you see the lower corner of my original matrix C. So the first line and the first row, first column and first row of my original matrix are deleted here. So I'm deleting the first row and column, and then I'm copying basically this submatrix from my C into this corner. So I have this matrix now, which I have the shifted values, and where I don't have any shift, then I put not the number there. And so then I'm comparing pixel by pixel. So I'm taking this one and this one, I'm taking this one and this 2, I'm taking this 2 and this 3, and I'm just comparing and making a tally how many times I have different pairs. And so here is how you do this tallying. So you start by defining your co-occurrence matrix to be a k by k zero matrix, and then you go over all grayscales in this I direction and all grayscale in this j directions. And so what you do is you are finding the pixels in your C where the grayscale value equals I. Then you are finding all pixels in your C shift where the grayscale value corresponds to j. And then you are choosing those pixels where you have I in the first and j in the second matrix. So I'm taking the dot product of those vectors here, and notice when I have a pixel in the original matrix that is value I, and in the second I have value j, so then this product is 1, otherwise it's 0. And so then I'm summing how many times I have 1 and 1, so that is exactly the number of co-occurrences. So I'm taking sum over i's and j's, and so then I get the tally. So this is giving me how many times I had the coincidence of I and j. And so this simple code gives you the non-normalized gray level co-occurrence matrix, and then you normalize by the sum, and that's the end of the story. So you see that forming this grayscale co-occurrence matrix is not difficult. You just create a shifted image, and then you compare pixel by pixel what the co-occurrence is in those images, and so that gives you the matrix. Now, once you have this co-occurrence matrix, gray level co-occurrence matrix, so if you want to analyze, so there are a couple of numbers that people have defined to analyze those co-occurrence matrices. One is called the contrast. So you have the G matrix. So now you can calculate the sum over all pixels multiplied by I minus j. So what does this I minus j do? So when you have I and j equal, then this coefficient I minus j is 0. So in this number C, pixels which are close to each other in color give 0 or small contribution, while pixels which are far away from each other in color give a large contribution. So this number here is large, means that there is lots of contrast in your picture. So therefore this variable is called contrast. This emphasizes the off-diagonal entries of the gray level co-occurrence matrix, because the diagonal entries are going to be 0, and entries close to the diagonal are having a small weight, while pixels off the diagonal are having a big effect. And so that means that you give a big weight to pixels which are far away from each other in the grayscale sense. And so this is called a contrast. So you can try to classify images, but just by saying what is the contrast. So if the contrast is big, you have one type of images. If the contrast is small, you have other type of images. Uniformity is basically the somehow the overall let's say let me see. The overall appearance of the image. So if you look at this uniformity, it's just the Frobenius norm of F. And so when you have, let's say, when you have a very uniform picture, so suppose you have a gray image. So that means that you have only one value at the diagonal. And since we are dividing by the sum, your matrix would be all zeros, and there's just one in one diagonal entry, right? Because there's just one gray level. And so the only possible co-occurrence is that the gray level is co-occurring with itself. And after scaling, you see that this number here is minimized if all entries are equal, and it is large if you have lots of gray level. So maybe it should be called non-uniformity in line with the concept. But so this is not our nomenclature. So people are using this word uniformity by this Frobenius norm. Okay, so that's one characteristic. So that tells you something about the image. I will show you examples soon so that you see how these work. Okay, so then we have homogeneity. Homogeneity is the opposite to the contrast. So this homogeneity is emphasizing diagonal entries and giving small weight to entries which are far away from the diagonal. So that means that if you have big differences in pixel values, so then this homogeneity is small, and if you have small changes, then this homogeneity is large. And then, of course, people are using entropy. Entropy somehow measures the kind of the randomness of the underlying image, and it turns out really that if you have a noisy image, typically this entropy is large. So entropy is some sort of randomness measure. So let's look at some pictures. So I have generated 4 types of simple images. So I think yes. So here, so we have, this is a white noise picture. So what I did, I drew the well, not really white noise, it's a noise picture. So I drew the pixel value from uniform distribution 0, 1 independently. So each pixel has a grayscale value, which is independently and uniformly sampled from interval 0, 1. So this on the left is the original picture. Then I reduced the grayscales so that I have only 8 different grayscales left. So I'm classifying each grayscale into according to in which interval they belong to. And with a bare eye, I don't see much difference between the left and the right picture here. So I'm not really losing so much visual information, at least in this reduction. And then I calculated the gray level co-occurrence matrix, and here it is as a bar plot. And so you can see that since this is a random image, so if I take a pixel and I take another pixel, I believe that this is 1-1 shift. So this is a diagonal shift. So if I take two pixels, the probability that I get any value is the same. So therefore this is pretty much uniform. So I have more or less equal occurrence of any possible pair of gray values here. And so this shows up in this grayscale co-occurrence matrix. Then I generated the noise with a smooth, let's say, white noise. I'm not going into detail how this was generated, but you see that this is some sort of a cloudy picture. It's a random texture, but it has, let's say, a correlation length which is not 1 pixel, but it's several pixels. So there is some sort of smoothness. I call this clouds. And so when I do the reduction of this picture into 8 grayscales, you see a little bit of staircasing in the grayscales. So here you really see that I'm reducing the grayscale dramatically. So now if I go and look at the grayscale co-occurrence matrix, I see that since this is sort of a smooth picture, so the probability of finding the same gray value after doing an offset is rather high, because it's smooth. And so therefore you see that this is diagonally weighted matrix. So the most elements are close to the diagonal. So in this picture it is very unlikely to jump from white to black, because it's a smooth picture. So when you go from white to black, you go through all the grayscales typically. And so therefore the off-diagonal entries like 8-1 and 1-8, they are essentially 0 here. They are probably 0 exactly. So I don't find 2 pixels close to each other so that one pixel is black and the other one is white. And of course I can change this situation if I take a longer offset. Because if I allow, let's say, a jump of, let's say, 5 or 10 pixels, then it starts to become more likely to find a black and white pair. But with a small offset, you don't find that. Here's a Gaussian function which I have first coarsened. So I have this staircase Gaussian. And so now you see that again, here, this is really a smooth picture. And so the probability of finding the same grayscale value is high. So this is strongly concentrated on diagonal. And 1 is 0, so there's lots of black in this picture. And so therefore, the probability of finding a black-black co-occurrence is high. And so you see that there's a high element in that corner of my co-occurrence matrix. And here is a stripe picture. So I'm moving from diagonally, and so you see, because of the regularity of this picture, when I'm moving one down and one left, I'm always jumping from black to white or white to black. And so therefore my co-occurrence matrix is completely concentrated on those two corner elements. One corresponds to moving from black to white and the other one to white to black. So notice, if I had chosen here my offset to be a horizontal offset, I would have a completely different co-occurrence matrix. So typically when you do these co-occurrence matrices, you shouldn't be just using one co-occurrence matrix, because that is sensitive to just one sort of structure. You should use always several of them to have an idea of what's in the picture. Nevertheless, this is serving me to show how these numbers that I defined work. So let's take the noise picture. So the noise picture typically has a high entropy. So entropy is measured in the randomness, and sure enough, the noise picture is really a random image. The clouds image was also a random image, but not that sort of random, and so my entropy is much less. Where stripes, for instance, is not random at all, and so the entropy is low. The contrast in the stripe image is large, and so it is in the noise image. So those two images are high contrast images, while the clouds and Gaussians are not high contrast images. A uniformity in the stripes is high, so it is a very uniform structure, while homogeneity is small. While Gaussian has a high homogeneity and clouds have high homogeneity, while the noise image has a low homogeneity. So you see that these numbers that I can calculate, they are somehow descriptive of what we are looking at. So they are certainly useful quantities to look at if you want to understand what's in the picture. So let's look at a more realistic case. So I have a texture database. So this is from a source in the internet. This is a Swedish database where they have texture images in 5 classes. They're called rock, lentils, canvas, sand, and seed, which is the upholstery textile. So it's called seed. And so I'm looking how these pictures are different from each other. So here is my I think this is rock. So this is just images of stone. And so here is always, in my pictures, there is always on the left there is the original picture, and next to it is the 8x8 coarsened image. And then I have the co-occurrence matrix with offset 1, 3, and then I have an offset 5, 5. So 1, 3 is I move 1 down and 3 to the right, and 5, 5 means that I'm moving 5 down and 5 to the right. Okay, and so you see that these co-occurrence matrices are somewhat different because they are sensitive to the granularity and the detail size in the texture. So when I'm changing the offset, I get different co-occurrence matrices. So this is the rock example. So I have one example of the rock. So these are image size. Image size here is 576 by 576 pixels. So they are pretty detailed images. And I have 40 images on each class. So my data is going to be 200 gray level co-occurrence matrices. I'm doing this for each image. And so I'm showing you just one example of each class. So here is the lentil case. So these are the image of lentils. And so you see that the two co-occurrence matrices are sort of diagonally weighted. That means that there is structure in my images which is at least typically 5 pixels in offset. So moving only 5 pixels off from the original pixel, you are likely to find a very similar grayscale. So that tells me that with that offset, the image sort of looks smooth. While if I look at this canvas, so in canvas, of course, the details are smaller, and when you're moving 5 pixels down and 5 pixels right, you will probably find already with a higher probability you will find a different grayscale, and so therefore this grayscale co-occurrence matrix starts to be less diagonal than the lentil case. So we see that there is a difference. Here is sand, and sand again tells me that, so if I take 1, 3 movements, so this is rather diagonal, but 5 movement is already spreading around the diagonal. So this tells me the detail size. So the detail size is maybe of the size, 5 pixels. And this is the seat case. So this is the upholstery textile, and so here are the grayscale co-occurrence matrices. And so now I'm asking a simple question here. So can I separate these? Can I separate these different textiles or textures from each other using these grayscale co-occurrence matrices? So what I have done is I took these grayscale co-occurrence matrices, which are 8 by 8 matrices, and then I'm reading them in a column-wise order. So I'm making them into vectors of length 64. So I have, for each offset, I have a data vector of length 64 corresponding to each one of these textures. So my data matrix is now 64 by 200 because I have 200 images. Okay, so then I'm asking, can I separate these different classes? And I'm using the most obvious way to look at the data. I'm using the principal component analysis. And so here are the principal component analysis pictures. So I'm calculating only the first 2 principal components. And then I'm taking the principal components of each one of those grayscale co-occurrence matrices. I'm plotting with different colors here. And so you see that they form nice clusters here. So this tells me that the grayscale co-occurrence matrix 1, 3 is at least capable of separating, let's say, lentils from blue one is, I think, canvas. So remember, lentil was where I had large details and canvas was where I had small details. And so if I'm looking at this 1, 3 offset, then clearly at least lentils and canvas are different. There is a little bit of overlap here with stone and sand, for instance, and seed. So these are not so clearly distinct clusters. I take the same data set, but then I'm calculating the 5, offset CGL grayscale co-occurrence matrix. And now you see that I have more separation. So I have lentils are always separated neatly. And so now I start to see a split between the seed, sand, and stone. So the sand and stone, they are the ones which seem to be sort of closest to each other. So this is sand, and this is stone. So you see, even visually, they are kind of close to each other. Okay, so then I take what I'm doing here now. I'm looking at the first and third principal components. So now the picture looks like this. So I get a little bit more separation. So this black cloud, which was, let's say, seed, starts to be separating. So the third principal component helps me to separate at least this seed. And stone and sand are always close to each other here. So well, let me see, stone and sand. So magenta and green. So they are close to each other. They are not overlapping here, but the green one is overlapping with the blue one. So what you can do now is you can okay. So here are the second and third, and you see that yes, there is clear clustering. So I believe that the gray level co-occurrence matrix is also capable of separating the sand and the stone, because if you look at these green and magenta clouds here, they're rather neatly separated. And so what I thought that I would have here, but I didn't. But so if you want to test, so take these two co-occurrence matrices G13 and G55, so they are 64 of length. Concatenate them together. So now you are looking at the data with two different offsets simultaneously. And if you do this concatenation, you get even nicer separation of the groups. So this is a little bit of experimental part. So when you're trying to figure out which offsets are separating your data, you should be experimenting with different offsets. And I realized that it's 5 o'clock. This is convenient because this is my last slide for today. So this is basically all I had for image mining this time, and we'll continue on Thursday then. So thanks everybody for joining today, and I posted these slides on the Teams folder, so you can download them there and read carefully, and you can go and see the data sets of these textures if you are interested in, and we'll see you on Thursday then. Thank you everybody for joining today. Bye.
Thank you. Have a nice day.
You too.
Ciao, arrivederci, grazie.
Grazie a tutti.
Thank you.
Thanks.